So this is the Advanced Extension Award from 2010. Now, why am I doing the 2010 paper and not anything more recent? You know, the big YouTubers are kind of frowning upon me immediately because they know that to get the views you need to do current and recent things, not go all the way back through the archives. There's a couple of reasons I'm doing 2010. Firstly, because the 2018 and 19 Advanced Extension Award papers are hidden behind the Pearson paywall, which I have access to, but I don't want to put it online for free when they clearly don't want it out there. So I'm not doing those papers until they make them free. And also, 2010 was actually, this was the very paper that I was given the opportunity to sit when I was in year 13. Now, I use those words carefully, given the opportunity to sit, because I didn't sit it. I said no when I was asked to, because it was the 30th of June, and I was in year 13, so I really wanted to just start exam leave. And I also just wanted to play cricket that day. Shout out to Roxeter CC, who I played a game for that afternoon, even though the paper was in the morning, but I didn't want to spend 3 hours in the morning and then go play cricket. I wanted to take the morning off. I think I scored some runs that day, actually, if I recall correctly. So it was time taken well out of maths. But 12 years later, let's come back to this and see how I would have done if I actually would have sat this, because if I wasn't just lazy. Question number one. This is a very, I'm going to be honest, this is a very easy question. I don't really know what it's doing on Advanced Extension Award. The idea is we want to square out these roots, so we're just going to square both sides. Just be careful to square both sides and not individual terms. So expand this out carefully and you get 3 squared is 9, plus 3 lots of this, plus another 3 lots of this. When you do the two things, you make 6 lots of it, and then this squares just to itself, obviously, underneath the surd. This obviously also square roots, the surd and the square cancel. If we rearrange that up and make this, then we can just square again. Because if we square again, the 6 squares to a 36 and this squares to an x plus 1, and then I just end up with a bunch of stuff that doesn't have a square root in it. It's a quadratic. I know I can solve quadratics. I'll tidy it up. I'll divide by 4 here, and I'll get answers of x is 0 or x is 3. Now, the only thing that you do need to do to get the last mark on this question, rather than just finish here, is you need to check that both of these are actually solutions. Because when you do this whole squaring thing, it's very possible to create fake solutions. And if you've practiced this kind of question before, you know what I'm talking about. So just test both solutions. When you put in 0, you get root of 16, which is 4, and 3 plus root of 1, which is also 4, so that's definitely a good solution. When you put in 3, you get, well, that's going to be 9, root 25, which is 5, and that's going to be 3 plus root 4, which is 3 plus 2, which is also 5. So both those solutions are good. So moving on to the second part. So yeah, we can bring this half up to the top here, because that's power law for logs. Then we're taking away these logs and these ones too, actually, so we can divide each term. So it's this over that, which I've written as a root now, and this over that. Now I've got 2 logs here, so I can just cancel them, and I end up with this. Now, I could square both sides of this if I wanted to, or I could cross multiply. I've got a couple of options. This is a 3-hour paper, so do not feel bad about trying something and not really working very well, and then trying something else. I've cross multiplied. So this just comes over here, this comes over here. And now, again, you could square both sides to get rid of this root x. But if you do that, you end up with some pretty horrific numbers. I'll just show you really quickly. You end up with this, which, I mean, this is a non-calc paper. If you want to try and go for this, go ahead. This is what I did first, of course, and then I realized that I wasn't really feeling in the mood to actually do this. So I thought, is there an easier way here? Well, of course there is. Let's just bring the 3 root x over, and then make a substitution, because this is just a hidden quadratic. If we make the substitution y squared equals x, then we can say that this is 2y squared minus 3y. Root x is now y, if we square root both sides there. And this is very simple for me to solve, much easier than this is. Once I've solved it for y equals minus 2 or y equals 7 over 2, I can then go back into here. Y squared is x, so square that for x is 4, and square that for x is 49 over 4. But again, just like with the previous question, you want to check whether these answers actually work. If you put x equals 4 into this, you get log of to base 3 of minus 3, which doesn't make sense. You can't do that with a log. So this is not a solution. But then when you put this one in, it's all fine. Everything is nice and positive and it's good. So that is the solution, and that's the first question done. I'm hoping when I was 18 I would have got that question right. Though, who knows? Who knows? I was more interested in playing cricket after all. Question number 2, so the sum of the first p terms in arithmetic sequence is q, and the sum of the first q is p. Now this is the sum of an arithmetic sequence where this is the number of terms n, a is the starting term, and d is the difference. It wants the difference in the first term, so it wants a and d in terms of p and q. So let's put in the information we know. When we've got p terms, so when n is p, the sum is q. So when we put in n is the number of terms is p, so p is everywhere. Here, the sum itself is q, and when we put in the number of terms as q, the sum is p. So I've got these two equations here. I think I just times everything by 2, and also just expanded out some brackets apparently. And I think I did that with the other one as well. And so we've got two equations here, this one, and it wants me to give them d in terms of p and q and a in terms of p and q. So essentially, I just need to use these two equations and eliminate a and d one by one. Eliminate a first to get this, and then d to get this. So I looked at these two things and I was like, oh, okay, what I'd like to do is just do this, take away this to cancel the a's, but they don't cancel because the p and q don't match. So let's just times this by q and this one by p, and then these two middle terms will match perfectly, and now I can just take away, and I'll get rid of the a's. Now this looks horrific, right? But it actually turns out alright, because for a couple of reasons. Obviously I can factorize out d from this kind of thing, and I can also factorize out pq to leave this. And this actually also factorizes, because you can take out a 2. By the way, this ends up being quite nice, because 1 minus minus 1 is, minus 1 minus minus 1 is 0, so that ends up being quite nice. This also factorizes to q minus p, q plus p. And now, almost for a second, you just immediately cancel these two things, but then you notice actually, oh look, one of them's wrong the wrong around. But that's okay, you can still cancel them as long as you introduce a negative in there. So one way to see what I've done here maybe is just to times this side, this 2 by minus 1 in order to also times this bracket by minus 1, because if you're introducing 2 minus 1s, that's just like timesing by 1. So I flip this bracket over in order to put a minus here, and then I can cancel it out with this one, and then just of course divide by pq, and we end up with this expression for d. And that's that one. And now for a, just take one of the expressions that you've got and substitute in this d with p's and q's. Now this is horrific again, but just get through it. It's a lot of algebra, just get through it. This p and this p cancel, which is fine. So this p minus 1 times by this to make, and then I've brought this minus out to here to put the minus there. So that's all okay. I haven't really done anything there too much. I'm trying to isolate a, remember. I times everything here by q just to get rid of the fraction. Then I moved all of this, I divided everything by 2 actually here because everything's got 2s. Then I moved all of this object over and then divided by pq. And this, I was a little bit unsure here as to whether this was right, because it's like not simple at all. But it is. That's the answer. That's just the best you can do with it. The fact that it's only 3 marks suggests that, yeah, I didn't really want to be writing too much more than just this, and unless there was some completely other way to go about it that gave you a better answer. But we'll just go with it. And now the sum of the first p plus q terms, well, that's just what happens when you do s, the sum of p plus q. So I'm just going to go into here and make n p plus q, except I can also of course make a this and d that, and that's going to give me something that just has p's and q's in it. And again, this is even more of a mess than anything we've seen before. Just deal with it very slowly and very carefully. So the first thing here I've done is I've just said, well, let's put this 2 into here in order to cancel out this 2. Oh, sorry, I haven't actually done that, have I? What have I done? Oh, I factorized out this pq, of course, to get rid of the fractions. So I factorized out this pq and put it at the front. Now what have I done? Now I've done some cancelling with the 2's, right? So I've cancelled this 2 with this 2 and this 2 because this one is dividing. I've brought this negative to the front here. I haven't done anything else. I'm making very small steps. Haven't done anything else. I think I'm confident at this point just to expand all this out and really hope that stuff starts cancelling. And would you look at that? Cancels, 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 cancels. It's just very satisfying to put these checks through everything. And you just get something that is absolutely lovely, because this PQ even cancels with that PQ, and you just end up with minus 1 times P plus Q for the answer. So I was quite satisfied when I got to that. And it like, even when I got to this question, I was a bit unsure about these answers, but when you see that at the end, you're like, oh, okay, so sure, I think I've got this right then, because yeah, this is great. Question number 3. So find an expression for the gradient of c. So gradient is of course dy by dx. So I'm going to differentiate this thing. F and g are not functions of x, they're just constants, so just be a bit careful of that. don't just do it on autopilot and pretend they're functions, because often f and g are given as the notation for functions. Do some partial differentiation. This differentiates to 2x, this differentiates to 2y, but stick a dy by dx there. And then product rule here, right? X differentiates to 1, so you just get fy. Y differentiates to 1, so you get fx, but you've differentiated y, so it's dy by dx. And then g is a constant, so it differentiates to 0. Collect the dy by dx's. I mean, this is just regular A-level maths, isn't it? And then the expression when x is alpha and b and y is beta, you just put those in and you get your expression. So yeah, that's about that. Given f is less than 2 and f does not equal minus 2, and that the gradient of this is 1, so essentially this here is 1. Show these things. Okay, well, let's sort of cross multiply here. And what I did here was I brought everything to one side. Again, this is one of those times where it's a 3-hour paper. I did a couple of wrong things here to start with. I started rearranging this for alpha and beta. Just bring everything to one side, and actually notice that this factorizes beautifully. Because there's some 2's and some f's and some alphas and some betas, but the 2's are always with alpha and beta, and the f's are always with alpha and beta. So that suggests that this factorization might work quite nicely, where the 2 distributes to the alpha and beta, and the f distributes to alpha and beta there. But if this is equal to 0, then that means either 2 is equal to minus f, but the question itself says that's not a thing, which told me that this was the right place to be going, because I've ran into something that the question told me about. Or, of course, alpha is equal to negative beta, which is the thing that I'm trying to show. So okay, that's the first bit then, clearly done. What about this bit, showing this bit here? Well, what I originally tried to do was substitute this into my expression for dy by dx. I was a bit confused, I think, about where I was going. A few things go wrong there. Firstly, you of course just get the answer of 1, because that was the whole point of doing this. But also, where are you going to get a g from? Now, the only place we're going to get a g from is if we go all the way up to the start, because as soon as we differentiated, we lost the g. So, okay, let's go all the way to the start. Let's substitute x equals alpha and y equals minus alpha in there, because x is alpha and y is beta, but beta is minus alpha, so we can just substitute in minus alpha for the y's. When you work with this, minus alpha squared is positive alpha, of course, so we collect that together. When you work with this, you end up getting something very nice, and when I say very nice, I just mean you get what the question is asking you to get, so that's good. Cool. Given f is negative 2, sketch C. Now, on these type of questions, it's almost always the case that parts A and B are really helpful in some way. But actually, as soon as you write this with f equals minus 2, alarm bells start ringing in your head, because you're like, well, actually, this thing just factorizes, doesn't it? This is just a very common factorization to know. It's this. So, okay, but now, of course, this is just this squared. Can I not just square root this? And be careful, when you square root this, you're going to get plus or minus g, of course. But this is just, I mean, x minus y equals g is just a line, like it's the line y equals x minus g. And then x minus y equals minus g is just another line. So actually, this sketch is just 2 lines, one with y-intercept of g and one with y-intercept of minus g, both parallel to each other. So quite an interesting sketch. Also interesting that you don't actually end up using any of this stuff. You can just put in the minus 2 and then just roll with it. But yeah, cool. Question number 4. So a vectors question, although I have to admit that I basically didn't use vectors for any of it. Mostly because I don't teach a huge amount of vectors, so I kind of ignore them where I can. I'm not too practiced with them. Just label everything that the question gives you, 5i, 10f, 20k. Now they're asking us to look at the triangle CAF. So that's kind of a triangle that's made here. I'll draw it out. It's kind of diagonally from there to there to there and then up to there again. But I can work out all of these lengths here because the length along the bottom is just 5 squared plus 10 squared square rooted, which is, and then the length along the side, C to F, I guess I started with, is 5 squared plus 20 squared, which is 425. And then F to A is 10 squared plus 20 squared, which is root 500. If you wanted to, you can simplify all of those things. I don't think it matters too much, but of course I'm looking for cos of CAF, so I know I can just use cosine rule here. And actually, the reason simplifying may not have been an amazingly helpful idea is because when you square this side, you just end up, of course, with 45, and this side with 500, this side with 125. It's useful here to cancel them down, because now these are nicer numbers to work with. But of course, when you do this, you just end up with, I'm sure you can follow my working here, cos CAF is 2/5. There's a way to do that just with vectors, but it's essentially cosine rule anyway. But yeah, I was just avoiding vectors because I don't really like them too much. I also avoided vectors here. So there's a point x here such that f to x makes a right angle with A to C. So just looking at my triangle I was looking at before, I just make a right angle here. But that's really helpful to know, because this right-hand side here, I have a right-angled triangle with a hypotenuse that I know, and an angle cos of f that well, I don't know the angle, but I know cos of f is 2/5. So actually, I can say cos of CAF is equal to this little distance here, a to x. I've marked this point literally as x, over 10 root 5. But I know cos of CAF, so that's just 2/5. So I can work out the length a to f. Now, they're not asking me to that. They're asking me for the length f to x, which would mean that I would need sine of CF. But that's okay, because I know that sine squared is 1 minus cos squared. So if I square cos to get this, and then do 1 minus that, and then square root it, I'll get sine. And so actually I can now use this to find the length of fx. I know I'm completely ignoring this for a second. I'll deal with this later. I chose to do this first, just because I spotted that I could deal with it first. If sine of that is that, then and sine of this is f to x, opposite over hypotenuse, I can just do this, cross multiply, and you get f to x is this. So that's the distance f to x. Again, just completely ignoring vectors because I can't be bothered. And now, what about the position vector? Well, position vector is O to x. So I'm looking for how to get to O to x, which is sort of on this diagram roughly here. Well, O to x is going to be, I think, okay, at this point I worked out the length A to x, which is going to be helpful. So I also know this length just by using the original cos that I had before. Now, how do I work out O to x? Well, it's O to A plus A to x. And now O to A is just obviously 5a. But A to x, what is that as a vector? Like, I know its length is 4 root 5, but if its length is 4 root 5, that makes it 4/5 of the total length of this base. Now, that, the picture doesn't make it look like that at all, but this length is 4/5 of the whole length, because it's 4 root 5 as opposed to the whole length, which is 5 root 5. So, and the entire vector A to C is, well, I would go minus 5i and then plus 10j, or 10j minus 5i, and A to x is 4/5 of that, based on these lengths. So I do 4/5 of that, which is this, and now of course O to x is just O to A, which I've already said is 5i, plus this thing here, and we get I plus 8j, I think, is our final answer, which is cool. So that's that. Last part. This is where I finally actually did use some vectors, because I'm very comfortable finding the intersections of line in vector form. So I've got one line which goes through the origin and the midpoint of this face here. Now, the midpoint of this face is 10 this way, 5 this way, and 10 up. Sorry, it's only 5 this way, isn't it? Because it's half of this 10j. So that's there. And the origin is obviously at 0, 0, 0. So this line has vector equation 0, 0, 0 plus k, lots of the difference between this position and this position, which is just this. Now, of course, I can simplify that to be that. Now, what about L2? That goes through A, which is position 5, 0, 0, and the midpoint of GF, which has position 2.5 across, 20 up, and 10 back this way. So that's going to be that position there. And now, of course, do the same thing. We start at this point, and then we add some amount of the difference between here and here, which is minus 2.5, 10, 20. Or you could have gone from here to here and done plus 2.5 minus 10 minus 20. It's not going to make a difference. Okay, and then I can, of course, simplify that to be this kind of idea. But now this line needs to intersect that line, which means this vector needs to equal that vector. And reading from the top line, we have this equation, and reading the second line, we have this equation. Notice how the third line is just the same as the second line. You just double it up. This is a simultaneous equation. Let's solve it for m by literally just making that 5k 10m and then solving. This is non-calculator. I think I doubled today, yeah, and then I times by 4 because I really couldn't be bothered to do a bus stop. 40 divided by 100 is 0.4, and then put 0.4 into your equation for L2 because we've solved for m, so it's useless here, and we end up with this as our point of intersection, which is cool. Okay, question number 5. So using a substitution, integrate this thing here. So okay, well, let's use the substitution they've given us. There it is. Let's rearrange it first a little bit to find u. So take away 1 from both sides and then bring this 1 over to there, and we get this for u, which is good. We also need to find dx. So if we differentiate that, we just get dx. That differentiates to 0, and this differentiates to minus, well, this is u to the minus 1, isn't it? So it differentiates to minus u to the minus 2. And then I've differentiated to u, so I'll put du. So okay, that's that. What else do I need? Well, I can start maybe substituting in now. So x minus 1 is 1 over u, I can see from here. I don't have x squared minus 1, but I teach enough GCSE maths to look at this and immediately write it as this. I have an expression for x minus 1, as I've already said. X plus 1 I don't, but if I just add 2 to both sides there, I will get 1. Now, I don't really want to substitute that in, so I'm just going to make it one fraction by timesing this by u over u, and then putting it together. And now I can put this into there, this into here, and then this into there, and I'll end up with this. Just be very careful when you're doing this. Expanding this stuff out seems like the most obvious first step. 1 over u is the same as just a u over here up at the top. This minus I brought out to the front, and then I wrote that as 1 over u squared. Now this u squared can cancel with this u just to put a u on the bottom here. And now when I root a fraction, I can root the top and the bottom separately. The root of that is of course just u, which will cancel with that u there. And I'll end up with this, which is a very easy integral to do. Because you can just write it as the power minus a half, and then literally just integrate using the normal rules. Raise that up by 1 to get positive a half. I actually just guessed this is the answer, and then noticed, tried to differentiate it to check what constant I need here. That's how I always do it. A half time, bring the half down to make a half there, times by 2 gives you just 1, and so this differentiates the correct thing with the minus there. Put the plus c, because I noticed there was a plus c here, and otherwise I would have totally forgotten it. But okay, that's good. Now I just need to substitute back in the x's. Now I don't have an expression for 1 plus 2u, but I notice I've got something helpful here. So if I just times this by u, I'll get this. And now u itself is 1 over x plus minus 1. So put that in there and you get x plus 1 over x minus 1 is this thing here, which I can just put into there, and I'll get exactly what the question wanted me to get, which is good. Next part, hence show this. So the integral of this, we've already said, is this. So I'm going to use this and put it in between sec beta and sec alpha. That's what I'm going to put in, and I'm going to hope that I can arrive at this thing here. Now there's a few things I'm noticing here. Firstly, I mean, let's put in the numbers. Good. So put in sec a couple of times, then take away what happens when you put in alpha a couple of times. But notice when I take away minus the whole thing, I'm just going to add it in. So that's where this plus has come from. Now sec is 1 over cos. So I can replace that there, and now what happens if I just try and simplify this? Well, this becomes cos over cos, so it's 1 plus cos over cos. Now this cos will cancel likewise down here. This cos can cancel with this one, to just leave you with this line and this line. If you're not comfortable with that, just do a bit of KFC, using this as a division symbol instead, and then you change it to a multiply, flip this one over, and you'll notice the coses cancel. What do we do with this then? Well, okay, we can put that in, and we'll get the same thing here with alphas, of course. Now I'm looking at this, I see cot, which is tan. So first thing I'm thinking is, somehow I need to get tan. Currently I have coses. Second thing I'm thinking is, I currently have the powers of half, and I don't have any powers up here. So maybe I need some squaring in here, and then if I had squaring in here it would cancel and end up with nothing. Also I see some half angles, a over 2, alpha over 2, beta over 2. So, well, if you see half angles, you need to think half angle formulas. Now, I actually don't know any of the half angle formulas. I just know this. But, I basically never remember any formulas in maths. I always just remember like one of them and just make sure that I can just derive all the others from it. So from here, I know if I replace sine squared with 1 minus cos squared, I can get this. And now, okay, if I add 1 to both sides, I get this, which looks very similar to this, except instead of 2x is beta. But that's okay, because I can just say, well, in this case, instead of learning the half angle formula, just learn that it's the same as the double. It's just what happens when you replace 2x with y, and therefore x with y over 2. And now we arrive at that, which is super helpful, because, yeah, I can just put this stuff into here, where beta is y. So that's just great. And likewise for here, where alpha is y. I can do exactly the same down here. So I did that, and then I thought, okay, well, that's solved a couple of problems, hasn't it? I've got beta over 2 and alpha over 2. I've also got squareds, and I like squareds because I'm hoping those will cancel. The last thing I need is cot, which is a version of tan, and so that means I probably need a sine squared, because cos squared divided by sine squared is tan squared, which would then become cot when you raise it to that. So that's great. I just need to make this into a sine, and I just go back to here and I think, well, what if I just done something differently? What if I just made that into the 1 minus sine squared? Where does that get me? Oh, it gets me to exactly the right thing. And I just do exactly the same thing. That becomes a cot squared, it square roots. You write the alpha one first because it's a positive and that's negative, which is what they want, and you get the answer. So yeah, really lovely. Again, that's one of those times you have 3 hours, you need to think about it critically, think of all the results that you know, and how they might be helpful, and eventually you will get there. Question number 6. Given that thing, prove that thing is maximum then. So this is the only question on the paper that I looked at and just genuinely for quite a long time had no idea what I was supposed to be doing. You're talking about maximum and minimums, right? So you want to differentiate this thing. You think about partial differentiation, but that doesn't really help because, like, I want to know when this thing is a maximum. And if you do partial differentiation, you won't get df by the thing. You'll get like dx by. Yeah, it just didn't end up working. I could have written over here, I guess, but it just didn't really work very well. And then I realized finally, okay, they've given me this thing. I should probably use this thing. If you rearrange this to be that, and then square root to be this, you can just substitute this into here, and now you have something that's very differentiable to think about maximum and minimums. So okay, do df by dx, just differentiate, bring the half down, differentiate the inside this for minus 4 cubed, and then take 1 away from that to get this. Now I want this to be 0 for maximum and minimums. What did I do here? Oh, I just tidied it up a little bit, didn't I? That's fine. I want this to be 0 for maximum and minimums. I factorized out there, which is fine. Yeah, just take a 2x out of this, and then, yeah, sure, that's fine. So now I've got a product, and the reason I wanted a product, this thing times this thing, was because, again, I want df by dx to be 0, so that means that either 2x is 0, or this thing is 0. Now, if 2x is 0, then x is 0, and again, looking at this thing here, that makes y plus or minus 1, because 1 to the power 4 is 1, or minus 1 to the power 4 is 1. Now, if that's the case, then this thing here has value 0 squared plus or minus 1 squared, either way is 1. So, okay, that's fine. Now, that's not really doing this, but that's okay, because, I mean, think for a minute why that's okay, if you want to. Because this is when it's at a maximum. And like all I've done is differentiate and said 0, so it could well be that this is the minimum instead. And the maximum could arrive when this bit is 0 instead. So now let's check when this is 0. And now this looks very complicated for a second until you read about 4 centimeters up the page and you see actually you could just replace this horrible thing here with a y squared, and that will give you exactly what you want to get. Square root, make sure you have a plus or minus in there. And we get, okay, so that's going to be our maximum then. And so what value is it? Well, okay, if x squared is equal to y squared, that means x to the 4 is equal to y to the 4, which means looking at this section here, that means 2x to the 4 is 1, divide by 2, and square root, and we get x to the squared 2 is 1 over root 2, which also means y squared is 1 over root 2. So if we look at this thing here, we put both of those things in there, and we get 2 over root 2, which is root 2. And that's our maximum value. It's nice that it's bigger than that. That, of course, makes this a minimum when x is 0 and y is plus or minus 1, and this is the maximum when x is equal to minus or plus or minus y. Good. On the same diagram, sketch, oh, this one is rogue, sketch the curve C1 and C2 with this. Okay, we can all sketch this. I'm hoping we can all sketch that. That's 1 mark. Now, if that's 1 mark, it only means you get 1 more mark for doing this. This is the point where I'm actually a little bit unsure what you're supposed to do here, except that I've spent enough time on Desmos and GeoGebra to know that all that happens when you do this is you get a more boxy circle like this. In fact, if you raise these powers up to like x to the 100, y to the 100, you essentially end up with a perfect square. It's quite cool. You should go on Desmos and try it out. But those will be my 2 marks, just because I know what that looks like. You could have, I guess you could have worked it out, because, you know, in here you have x and y values that are less than 1. And so to add up to b1, you need to get them progressively closer to 1 all the time, because when you raise the power 4, you get smaller and smaller, quicker and quicker. So you need to get everything very close to 1 in order to have a chance of getting to this. I don't know. You probably could have worked that out, but whatever. Work out the equation of this circle C, 3, center of origin, which touches the curve C1, which is this one, at x equals plus or minus y. So a line like this is x equals y. So we want a circle that touches the curve there. So it's going to be a slightly bigger circle than this one. But we already worked out that when x is equal to minus y, or x is equal to y, in the previous page, take a look back if you want to, that means that x squared was 1 over root 2. Because you say, okay, that means x to the 4 plus x to the 4 is 1, 2x to the 4 is 1, divide by 2, square root, and we end up with this. But that, of course, means that when you add it with y squared, which is also the same as x squared, you get 1 over root 2 plus 1 over root 2, which we already discovered was root 2. And look at that. That's the equation of a circle. So we're done. Good. Cool. Last question on the paper then. You look at this, you think compound angle formulas, so you bring those out, you use them. Cos of pi over 4 is 1 over root 2, and so is sine of pi over 4, so we replace those all with that. So these are all 1 over root 2's, which just means I divide by root 2. At this point, what I did was I took that bracket and I took out a 1 over root 2. Now, root 2 times 1 over root 2 is 1, and that just got rid of all of these root 2's. So that's fine. I did the same thing here, and what's nice about this is all timesing, right? So I can times this by this, and I just get 1 over 2 at the front. And then I also, at the same time, so I brought this over there, then I expanded this. So root 2 times root 2 is 2, root 2 times sine x, and then root 2 times cos x, and then all the way along. Stuff cancels here, it's great. Lots of things go away, you end up with this. Sine squared doesn't cancel, but sine squared is 1 minus cos squared. So I can do that. 2 minus 1 is 1, and then cos squared plus cos squared is 2 cos squared. And now I can put the half back in, and now I sort of see how this is probably hopefully going to be that. Let's just hope that it isn't right down. I mean, no, it's fine. You can check that it does. When you square this, 1 over root 2 times 1 over 2 is half. You end up with 2 of this times this, which does end up being this, as we actually already saw in the previous question. 2 lots of 1 over root 2 is root 2, kind of interesting. And then cos times cos is cos squared, good. So that's that bit. Find the range of the function. Okay, well, the range of the function is all of the values f of x can take. Now, the biggest f of x is going to ever be is when, I mean, this is just something squared. So when cos is as big as possible, we're going to get the biggest function. So when cos is 1, we'll end up with this squared. Now, I worked with this. I made it a bit simpler and made it into that. So that's the biggest the function can possibly be. The smallest the function can be is when cos of x equals 1 over root 2. Sorry, equals negative 1 over root 2. Because that makes f of x was 0, doesn't it? And 0 squared is 0. Now, why can't f of x, why was I not trying to make this negative, like with a cos equals negative 1? Well, because even if you made the inside negative, when you square it, you still end up with a positive. So the smallest I can make f of x is just 0, and it's between that and that will be my range. Good, so the picture backs that up. It gives you the picture on the next page, and it backs up that f of x can't be less than 0, and these maximum points are clearly the points that I just found. Find all the coordinates of the maximum minimum, see maximum and minimum, you start differentiating, so let's differentiate this, bring the 2 down, differentiate by the inside of that, which is minus sine, and then bring the 2 down to a 1. We want stationary points, so we want this to be 0, which means we either need sine of x to be 0, or we need this to be 0, because again this is a product, so one of them has to be 0. Sine of x equals 0 at 0, pi and 2 pi. I hope we just know that without having to draw the graph. Here we want cos of x to be, and then it says coordinates. So I said, well, that's 0, it's this. We already figured that out. At pi, well, you just need to put pi into the function. Cos of pi is minus 1. I'm sure they probably would have given you the marks if you just left it like this. I expanded it out like a pleb, and then put in that value. So x is pi. F of x is this, and then at 2 pi clearly it's just going to be this again. Here, that means cos of x is minus 1 over root 2. Get out the cos graph if you need to. You know cos inverse of 1 over root 2 is pi over 4. We've seen that a couple of times in this very paper, which means if you're looking for minus 1 over root 2, you're looking to be this value here by symmetry, which is between pi over 2 and pi, which is 3 pi over 4, 3/4 pi. And likewise, you're also looking for this one in between pi and 3 pi over 2, which is 5 pi over 4. Again, if you're taking AEA, I'm sure you're very comfortable finding all those solutions. Okay, so at this point, we substitute those values into the function, except we can see from the picture the function is 0 here. So I'm just going to be lazy and say that it's 0. Yeah, good. So you could have substituted in, but if you had, of course, you'd have immediately put this into cos, which equals this, which immediately gives you 0. So yeah. Okay, so that's all the maximum minimum done, and I think that's the whole thing. This is the very last part of the question. It wants the area of R, so clearly some integration is going to be necessary here. These are rogue values here. They should not have come into the picture yet. I think I'm about to work out what those are, so ignore these 2 bits for now. If you're going to work out the area of this region R, you're going to need this intersection and this intersection, so I'm going to need to know when f of x is equal to 2. So putting f of x equals to 2, square root, remember the plus or minus, take away 1 over root 2. I tidied this up here, so root 2 is the same as 2 over root 2. So this is either minus 1 plus 2 over root 2 or minus 1 minus 2 over root 2. The minus 1 plus 2 gives you 1 over root 2. We've already seen here this gives you causes pi over 4 or 7 pi over 4. Again, thinking about the picture before, in fact, I'll just go back to it really quickly. Pi over 4 is here, or 7 pi over 4 because it's pi over 4 back from 2 pi, to give you that one there. So that's where I got that from. And here, of course, minus 1 minus 2 is minus 3, but minus 3 is bigger than root 2, so this is bigger than minus 1, or actually less than minus 1. It's not going to have any solutions. And that makes sense because, of course, I can only see two intersections here in this range. And the solutions are at pi over 4 and 7 pi over 4, which I should have animated in now, but who cares? It's fine. There they are. So how am I going to find this region R then? Well, I'm going to find the area of this box and then take away the integral of the curve between those 2 points. So this box has area 2 because its height is 2 times this minus that, the distance between them. Now this is 6 pi over 4, which is 3 pi over 2, times by 2 is just 3 pi. So the red box is 3 pi, and then my region R is just going to be the box take away the area of the curve from pi over 4, 7 pi over 4, which is the integral of the curve between 7 pi over 4 and pi over 4. I worked out about halfway through typing all this that it would have been quicker to just slash everything in half here, and then I could have just taken half of the red rectangle and then taken away the integral between pi, because I know that point there by symmetry is pi, also based from the previous part of the question, and then I could have just times the answer by 2. That would have just been a bit easier because it's easier to substitute in pi to whatever I'm going to get here than it is 7 pi over 4. But I wasn't really thinking about that because I'm quite comfortable working with this anyway, so it wasn't in the forefront of my mind. But anyway, the entire question and the entire paper now finishes by just working out this integral. So okay, let's expand this thing out, which gives you this, which you actually already knew because you'd done that in like part A. You'd gone backwards from this to this. I'm completely comfortable integrating this, completely comfortable integrating this, not so much this, but again, we've already seen how you can get rid of a cos squared. This is something we used before, so just divide by 2 and you end up with this substitution here. And I'm perfectly comfortable integrating all these things now. So of course, half plus half is 1, which integrates to x. This integrates, cos integrates to sine, so it just becomes a sine. This integrates to sine 2x over 2 times by this 2 is over 4. And then we substitute in. Again, I'm very comfortable doing all of these values off the top of my head. If you're not, that's why it would have been a bit easier maybe to work with just pi here and double the integral at the end. Just bring out the sine graph if you need to. 7 pi over 4 is pi over 4 back from 2 pi, which is going to be, for the sine graph, negative 1 over root 2, because sine of pi over 4 is 1 over root 2. 7 pi over 2 is 3.5 pi. So you go forward 2 pi, go forward another pi, that's 3 pi, go forward another half a pi, and you get to minus 1. These ones I'm sure we're more happy with. Sine pi over 2 is clearly just 1. And this is just I was just very careful here to get rid of these brackets properly. These twos obviously cancel nicely, which is good. And you end up with your answer eventually of 3 pi over 2 plus 5 over 2. So really nice. I kind of wish that I had spent the morning doing that 12 years ago, because I would have got full marks apparently, which would have been braggable.